In this video, we're going to take a look at how to evaluate trigonometric integrals involving the product of even powers of sines and cosines. The key to doing this will be the half-angle identities for sine and cosine. As a quick reminder, those half-angle identities state the following. Sine squared of theta can be rewritten as 1/2 times the quantity 1 minus cosine of 2 theta, and cosine of 2 theta can be rewritten as 1/2 times the quantity 1 plus cosine of 2 theta. These two identities will help us to rewrite even powers of either sine or cosine in terms of simply the cosine of double the original angle. One of the key steps for evaluating integrals with even powers of sines and cosines will be to evaluate the integral of cosine of 2x dx. This is a relatively simple integral, but there is one thing that we need to pay particular attention to ensure that we get the correct value when we evaluate it. In this case, what we might want to do is do a very simple substitution, with u being 2x, the function inside the cosine function. Once u is 2x, we know that du is going to be 2 dx. And since we don't have a constant of 2 here, we're going to divide by it and get du over 2 equal dx. We can now substitute everything into our integral, and we're going to get the integral of cosine of u du, and the 1/2 can be pulled out front. We can then find an antiderivative of cosine of u, which is we know to be sine of u. And as with any substitution, the last step is to go back to the variable x. And so we get 1/2 sine of 2x all plus c. And so the key thing we have to remember is that when we integrate cosine of 2x, we do get what we might think we would get as sine of 2x, but we do have to also multiply by the 1/2. And everything here holds true if the 2 is a different number. So for example, let's say this number instead of 2 at the original integral was 4. That just changes all of the 2's in our example to 4's. U would be 4x, du would be 4 dx, du over 4 would equal dx. Then we would have a 1/4 as our constant throughout. And so whenever we take cosine times a constant times x and integrate it, we're going to get sine of that constant, we're going to get sine of that constant times x divided by that constant. So let's take a look at the integral of sine squared x dx. Our first step is to use the half-angle identity to rewrite sine squared of x as 1/2 times 1 minus cosine of 2x. This integral is one that we can now find an antiderivative of. We have a constant multiple of 1/2, which we'll leave as is. The antiderivative of 1 is simply x. And by the little example on the previous slide, we know the antiderivative of cosine of 2x will be 1/2 sine of 2x. And of course, plus c. And if we wanted to, we could distribute this 1/2, although not necessary, and get 1/2 x minus 1/4 sine of 2x, all plus c. And this would be the value of our integral. So once we were able to rewrite sine squared in terms of just cosine of 2x, the antiderivative was relatively straightforward to compute. In this example, we'd like to evaluate the integral of sine squared of x times cosine squared of x dx. Our integrand here consists of sine squared and cosine squared multiplied together. We have half-angle identities that allow us to replace each of those factors with different expressions. And so we're going to use both of the half-angle identities here in order to rewrite this integral in a useful way. And so we have sine squared of x first, and we know that sine squared of x is 1/2 times 1 minus cosine of 2x. And we're multiplying that by cosine squared of x, which we know is 1/2 times 1 plus cosine of 2x. And so here we've used both of our half-angle identities to replace our two factors with different expressions. We have two factors of 1/2, which multiply together to give 1/4 that we can then pull outside of our integral. And what's left is simply 1 minus cosine of 2x multiplied by 1 plus cosine of 2x. We can multiply these terms together inside the integrand, the 1 minus cosine 2x and the 1 plus cosine 2x. And when we do that, we get the expression 1 minus cosine squared of 2x. At this point, we need to be a little careful. In the previous example, we ended up with simply cosine of 2x here, and we were able to simply find the antiderivative of that and be done with our problem. Here, however, we have cosine squared of 2x, and we don't know the antiderivative for cosine squared. In fact, that's the point of this video, is to find even powers of sines and cosines and find their antiderivatives. And so what we need to do is we need to use the half-angle identity for cosine squared once again, but we have to be careful because it's now cosine squared of 2x, not cosine squared of x. And so using that half-angle identity, we see that the cosine squared of 2x is going to be 1/2, 1 plus cosine of 2 times that angle, and so 2 times 2x will be 4x. And so this is just the half-angle identity for cosine squared that we previously mentioned, with theta equaling 2x. And since theta is equal to 2x, 2 times theta is going to be 4x. And so we're going to substitute this expression into our integral for cosine squared of 2x, and then evaluate that resulting integral. So picking up from where we left off with 1/4 integral of 1 minus cosine squared of 2x dx, we substitute in the expression for cosine squared of 2x, and we obtain 1 minus 1/2, 1 plus cosine of 4x dx. We can distribute the 1/2 here across that sum and simplify this to be 1/4 integral of 1/2, which is the 1 minus 1/2 that we would get when we combine the constants, minus 1/2 cosine of 4x. At this point, we can actually find the antiderivative of this integrand. We're going to have a constant, of course, of 1/4 out front. 1/2 has an antiderivative of 1/2 x. And then we know that cosine of 4x will give us a sine of 4x, but we need to divide by 4 find the antiderivative, and we also already have the factor of 1/2 out front, and so this is going to be a 1/8 sine of 4x, all plus c. And again, this would be perfectly fine as a final answer, but if we wanted to distribute the 1/4 and clean this up a little bit, we would get 1/8 times x minus 1/32 times sine of 4x, all plus c.